So I suppose what I'm trying to do, and I'm sure this is just a red herring, but let's go with it anyway, is I'm trying to take an image of something with a particular type of camera, say with a certain size pixel, and let's measure everything in pixel lengths, so this would be 1 unit long, and then whatever this pattern of light is, I put it through a lens, focal length f, and let's imagine the wavelength of light is lambda, and again the wavelength and lambda would both need to be measured in this length unit, whatever it is. And I have the Fourier plane, which I know to have a scaled Fourier transform. So here it is. This will be a blown up Fourier transform of whatever we've got there. But I think it would be, what I kind of want to do is I want to have the Fourier transform in the same units as this. So I'm going to have to shrink this down by a factor of f lambda, and only then, if I then do that, then the lengths will be the same. So in other words, the blocks block to block will be the same, only this will correspond to a unit in u, and that will correspond to a unit in distance. And the reason why this would be a good idea, if I could do this, if I could shrink it down like this and keep the same n across and n here, is I could then use I could take this, if I knew the phase, and do the fast Fourier transform to this, and I could just compare like my image in the Fourier plane with the computed fast Fourier transform. That'd be kind of interesting to do that, to see how close it is. And also it would greatly simplify some sort of phase retrieval algorithm like the Gershberg-Saxon algorithm, which I kind of I'd really like to do a version of that working, so I can just see how hard it is to make it work. At the moment I haven't got anything working. But let's imagine then, for now, let's imagine the camera we're using is a Ximea. Now, Ximeas have got 5.3 micron pixels, and let's stick with the idea of using a 3000 micron focal length objective, and for my f and for my lambda, let's stick with red light, which is 0.633. Well, for a helium neon laser, for example, so let's just go with that as a sort of figure. Now, if I'm converting it into this unit, I need to divide both of those by 5.3. And if I do that, I get, let's see, 3000 divided by 5.3 times 0.633 divided by 5.3 gives me 68. So I've got to reduce it, shrink it 68 times. So the problem I'm going to get then is that if I'm in my Fourier plane, and let's imagine my Ximea, that most of the action in my, let's say in my Fourier plane is, supposing it's 1000 by 1000, let's just say that's how many pixels it is with this particular lens. And when I shrink that lens, that image is going to go down to 1000 divided by 68, which is 15 pixels. So we're literally going to go down to something 15 by 15 pixels big, and so 15 by 15 pixels. So all of this data, all of this sort of variation is going to be sort of turned into 15 by 15 pixels, but those pixels in u, so 1 unit in terms of length, 1 unit in u, would be the same sort of physical size as a unit in x on the other side. So if I was to say pad that out so that this is the same as that, after I've done my shrink, then I could in principle directly do the fast Fourier transform on this, and the middle 15 set of pixels. I can't really say anything obviously about anything else. In fact, I didn't need to pad it out because I needed to compare the center ones. I could say that those 15 pixels should agree with the fast Fourier transform at least. What I don't really like about this is the way that I have lost a lot of information about the detail of these, because I'm shrinking these down. So you know, if this is the NA of whatever I'm looking at, I've kind of enormously reduced the resolution in Fourier space of my essentially by shrinking it, I've reduced the resolution. Let's try a different camera. Let's say I took the an Orca flash, say. I think an Orca flash has got 6 micron pixels. Let's take the same camera. So I've got 3000, an objective at 3000 divided by 6, and same light again. This is not going to be much different. Then my conversion factor would be roughly 53 times. So I still have this big shrink that I seem to have to do if I want to sort of combine the fast Fourier transform in this way. So another approach, rather than shrinking my Fourier plane, would be just to keep all of the detail in my Fourier plane. So here it is. Remember, my Fourier plane is stretched, it's enlarged by this factor of f lambda. So I've got all of this detail and this sort of enlarged. You see, the Fourier transform has been enlarged to that degree. So I could, rather than shrinking this one, I could enlarge my image by the same factor. So if I enlarged my image by, is that right? No, I don't think that's right. I think I would need to shrink my image by the factor, because by shrinking by that factor, that has the effect of enlarging the Fourier transform. So I could keep my Fourier transform as it is with all of its detail, but at the price of shrinking. I mean, look, a way of thinking about it is, if I shrink an image, then I increase the spatial frequencies. So imagine I've got an image like that, where that's the spatial frequency, and I shrink it, then the spatial frequencies are getting closer together. So the act of shrinking an image is the same as the act of inflating the Fourier transform. So I can shrink the image, but then I lose a lot of my nice image data in my image. But then I don't have to do anything to my Fourier transform. What I really want is to get to a point where the relevant information in my image and the relevant information in my Fourier plane are roughly the same, so that I can do a Fourier transform from one to the other using the fast Fourier transform. So just to be clear about that, if I shrink my image plane, if I do that, then this is equivalent to expanding and inflating my Fourier plane. And if I expand my image plane, this is equivalent to shrinking my Fourier plane. And if ultimately we have the same set of pixels in both, then this will create a problem, because ultimately one of those sets of pixels needs to be binned. So my question then would be, is there some optimal intermediate where I keep the sort of maximum information in kind of both, so I don't massively reduce and bin all of the pixels in the Fourier space, so I've got hardly any information left there, and I don't massively bin all my information in my image space, so I have no information left there. And I don't know the answer to that.